The lake did not flood. Its air killed at least 1,700 people. On the evening of August 21, 1986, Lake Nyos in northwestern Cameroon released a vast cloud dominated by carbon dioxide. It crossed the crater rim and moved down nearby valleys, reaching homes, farms, and roads with little of the wreckage people expect from a disaster. There was no lava advancing on the villages and no conventional explosion tearing buildings apart. Many structures remained standing while people and animals lost consciousness. The central mystery was therefore not what had been destroyed, but how an apparently quiet crater lake had turned the atmosphere itself into the hazard. Lake Nyos lies in the Cameroon volcanic line, a chain of volcanic features extending across the region. The lake occupies a steep-sided volcanic crater, or maar, and reaches roughly 200 meters at its deepest point. Rain and streams feed the surface, while deep geological pathways deliver carbon dioxide into water near the lake bottom. That combination matters because tropical crater lakes can remain strongly layered. Warm, dilute upper water may circulate seasonally without mixing all the way into colder, denser, mineral-rich water below. From the shore, the dangerous inventory was therefore hidden beneath a surface layer that could look entirely ordinary. The disaster began during an ordinary evening in farming communities around the lake. People were at home, walking along roads or tending daily work when some witnesses heard a rumble and saw a disturbance near the water. The exact initiating event remains uncertain, and responsible reconstructions do not turn a landslide, storm, or small volcanic disturbance into a proven trigger. What investigators could establish was the result. Deep gas-rich water rose, pressure fell. Dissolved carbon dioxide came out of solution, and an accelerating release sent lake water and gas upward. The violent outburst reportedly displaced water high onto the crater surroundings, even though the main lethal force was the gas cloud. Carbon dioxide is colorless, and in high concentration it can be lethal without leaving the burns, blast wounds, or collapsed walls associated with fire and explosives. The cloud from Nyos followed low ground toward populated valleys. People rapidly lost consciousness as breathable air was displaced and carbon dioxide levels rose. The official United States investigation concluded that death was caused by asphyxiation. Some survivors were found with skin lesions, but investigators attributed many of them to pressure sores caused by long immobility while unconscious, rather than to an exotic chemical weapon or hot volcanic gas. This medical evidence helped separate the real mechanism from frightening early rumors. The human toll was immense. Scientific and official reports commonly state that at least 1,700 people died, with thousands of livestock also lost. Exact totals vary among later accounts, so this documentary keeps the official minimum rather than presenting a disputed number as perfect. Rescue teams entered communities where buildings still stood, but normal activity had stopped. Survivors who regained consciousness could not immediately explain what had happened because the agent was invisible and the event had passed. The absence of ordinary damage made the scene harder to interpret, not less severe. It also demanded unusual care from responders who could not assume the air around every low place was safe. Nyos was not the first warning from a Cameroonian crater lake. In August 1984, a gas release at Lake Monoun killed dozens of people along a road. That event was still being studied when Nyos occurred 2 years later. Before these cases, catastrophic gas bursts from deep tropical lakes were not a familiar category in hazard planning. A volcano could be watched for earthquakes, ash, or lava, but a stable-looking lake storing dissolved gas required different instruments and a different mental model. The paired disasters changed limnology and volcanology by showing that the dangerous reservoir could be water itself, charged slowly from below. The storage mechanism begins with pressure. Carbon dioxide entering the deepest water is more soluble under the high pressure found near the bottom. Cold, dense water can hold the gas, while the lake's strong chemical and thermal layering resists complete overturn. The upper layer of Lake Nyos, roughly the first 40 to 50 meters before degassing began, behaved much more like the visible lake people knew. Beneath it lay stagnant water with far higher concentrations of dissolved carbon dioxide, iron, and other dissolved material. Sampling only near the surface could therefore miss the hazard. The crucial evidence lived in vertical profiles, measurements of temperature, chemistry, and gas pressure at many depths. Isotopic and chemical evidence pointed to a deep magmatic source for most of the carbon dioxide. That does not mean a conventional volcanic eruption blasted through the lake on the night of the disaster. The multidisciplinary investigation found no significant direct volcanic activity associated with the release. Instead, carbon dioxide migrated upward through geological pathways and accumulated in the lake's deep water over time. This distinction matters visually and scientifically. The true system was not a glowing magma chamber suddenly detonating. It was a slow recharge process, an invisible dissolved inventory, and a water column capable of preserving that inventory until stability was lost. Exactly what started the runaway release on August 21 remains debated. A local disturbance could have lifted some deep water, but the evidence does not securely identify one trigger. Investigators considered possibilities including a small landslide, unusual cooling, wind, rain, or internal water movement. A truthful account keeps those as hypotheses. The better established part is the feedback after gas-rich water began rising. As pressure decreased, bubbles formed. Bubbly water became more buoyant, rose faster, and brought still more carbon dioxide toward lower pressure. The process could therefore amplify itself even if the initial disturbance was modest. The physics resembles opening a shaken carbonated drink, but at the scale of a deep crater lake. In a sealed bottle, pressure keeps much of the carbon dioxide dissolved. Release the pressure and bubbles grow, lifting liquid as they expand. At Nyos, deep water rising through the lake experienced the same basic pressure change. Gas expansion accelerated the upward flow and helped drive a fountain-like eruption. The analogy explains the feedback, but it should not trivialize the event. The lake held an enormous natural inventory, and the surrounding crater and valleys directed the released gas toward communities rather than dispersing it immediately into open air. A concentrated carbon dioxide cloud can be denser than the surrounding atmosphere, so terrain becomes part of the disaster. Instead of rising like hot smoke, the Nyos cloud spilled over the crater and moved downhill through valleys. Low roads, hollows, and homes lay in its path. As the cloud mixed with normal air, it gradually diluted, but close to the lake, and along protected low ground, the concentration remained deadly. This is why a map of elevation and drainage explains more than a dramatic picture of the lake alone. The hazard traveled according to gravity, topography, and mixing, turning the quiet shape of the landscape into its route. Scientists arrived with a problem that crossed several disciplines. Geologists examined the crater and searched for evidence of fresh volcanic activity. Chemists sampled water and gas at different depths and analyzed isotopes. Limnologists reconstructed the lake's layering, while medical investigators compared symptoms and injuries with known effects of carbon dioxide exposure. The combined evidence converged: stored carbon dioxide from deep geological sources, a catastrophic lake release, a dense cloud flowing into valleys, and deaths caused by asphyxiation. No single photograph could prove that chain. The conclusion came from chemistry, sediments, water profiles, eyewitness accounts, and medicine fitting the same mechanism. The investigation also found that dangerous concentrations of carbon dioxide remained in the deep lake after 1986. Waiting for the gas to disperse naturally would leave communities exposed while recharge continued. Engineers therefore needed a way to lower the inventory without causing another uncontrolled release. Experiments led to a self-siphoning degassing system. A pipe reached roughly 200 meters into the lake. Once gas-rich bottom water was brought upward and bubbles began forming, expanding carbon dioxide drove the flow without a conventional pump. The fountain above the raft was not spectacle for its own sake. It was the stored pressure being released at a controlled location and rate. A permanent pipe began operating in 2001, and two more were added about a decade later to accelerate gas removal. The system changed both risk and the visible lake. Deep water carried dissolved iron to the surface, where contact with oxygen produced reddish-brown material. Monitoring showed the chemical structure evolving as the deep gas inventory fell. Degassing was not a one-time repair, because carbon dioxide continues to enter from below. Later research focused on balancing natural recharge with controlled discharge, maintaining the pipes and watching the water column so the safety system remains matched to the lake rather than abandoned after the emergency fades. Lake Nyos also contains a separate physical concern, a narrow natural dam of relatively weak volcanic material at the outlet. Researchers warned that erosion or failure could create a major flood downstream. Gas and dam risks are different mechanisms, and combining them into one vague threat would be misleading. The first is an invisible inventory dissolved at depth. The second is the stability of the crater rim holding back water. Both show why a landscape that looks static can contain processes unfolding on very different timescales. Monitoring must therefore follow the actual structure: water chemistry, gas recharge, pipes, lake level, and the natural dam, not merely the absence of another headline event. Lake Nyos changed the definition of a natural disaster. The event was not a conventional volcanic eruption, not a poison attack, and not a flood. It was a rare failure of a layered lake storing geologic carbon dioxide under pressure. At least 1,700 people died because the invisible cloud followed the land into their communities. The lasting answer was equally unusual: measure the hidden inventory, release it gradually through engineered pipes, and keep monitoring the system that creates it. The lesson is not that every crater lake is a silent bomb. It is that hazards remain invisible when we measure only the surface and assume a quiet landscape has no memory below it.